Dear student, today we will learn about this article number 13.3, force on a current carrying conductor in a magnetic field. This is very easy topic. So if we just first of all understand this figure, that is the figure number 13.12, then generally we get the idea. So I will give you one instance. Already in your childhood you have played with the magnets, and what is the idea about that? Magnets, if you just bring two magnets very close to each other, what will happen? They will repel each other or attract each other, so generally the force will be applied. So here the same thing is happening. This is the main theme of this experiment, is that here it is written here, a current carrying conductor. When we have started this chapter, we have already get the knowledge, we have already acquired the knowledge, current carrying conductor behaves as a magnet. So here you can see, according to this arrangement, this conductor is carrying current, so it will behave as a magnet. So this is a virtual magnet, and there is a real magnet. So obviously there will be interaction in between the two magnets, as according to our arrangement, the natural magnet, which is in the red color in this figure, that is fixed, that cannot move. By some glue or other arrangement we have fixed that. So now the remaining conductor, which is now here the virtual magnet, is hanging by the wire, so it is movable, so it can move. So when there will be interaction in between these two magnets, then which magnet will move? This magnet will move, which is the current carrying conductor. So if you bring two magnets very close to each other in between the magnetic field region, then there will be interaction. So that is the main theme of this experiment. So we'll read that. So here we'll read.
We have learned that an electric current flowing through a conductor produces a magnetic field. The field so produced exerts a force on a magnet placed in the vicinity of the conductor. French scientist André-Marie Ampère, 1775186, suggested that the magnet must also exert an equal and opposite force on the current-carrying conductor. The force due to a magnetic field acting on a current-carrying conductor can be demonstrated through the following activity.
Okay, now we have to read this activity.
Take a small aluminium rod AB of about 5 centimeters. Using two connecting wires, suspend it horizontally from a stand, as shown in Fig. 13.12. Place a strong horseshoe magnet in such a way that the rod lies between the two poles with the magnetic field directed upwards. For this, put the north pole of the magnet vertically below and south pole vertically above the aluminium rod.
Now you can see in this figure, so this magnet, what is the horseshoe magnet, which is in the red color in this figure, that is vertical. That means this north pole is lying with the base of this arrangement, and S pole is above that. Okay, so we have placed the horseshoe magnet here vertically, and in between this space, S, south pole and north pole, this current carrying conductor we have suspended. Okay, that is horizontal. So what is the arrangement? So horseshoe magnet is vertical, so above the north pole there is the south pole. So what is the magnetic field direction here? So this is north to south. Okay, and this figure, this conductor is lying horizontally. According to figure, you cannot assume that it is horizontal, but you just assume, you just consider it is horizontal, and it is hanging in between the south pole and north pole.
Fig 13.12. Connect the aluminium rod in series with a battery, a key and a rheostat. Now pass a current through the aluminium rod from end B to end A. What do you observe? it is observed that the rod is displaced towards the left. You will notice that the rod gets displaced.
Okay, here it is written that it will be displaced towards the left. How it will be, why it will be displaced towards the left, we'll get that idea after some time. Displaced. In which direction it will be displaced, we will learn after some time. Okay.
Reverse the direction of current flowing through the rod and observe the direction of its displacement. It is now towards the right. Why does the rod get displaced?
If the direction of the current will be changed, then the direction of the force applied on this current carrying conductor also be changed. Again it will be changed by other way if the direction of the magnetic field will be changed. If you place the south pole below and north pole above the south pole, then also the direction of the force applied on this current carrying conductor also be changed. If force applied on the conductor will be changed in two ways: if we change the current, direction, and if we change the magnetic field direction. Okay, now it is written here.
The displacement of the rod in the above activity suggests that a force is exerted on the current-carrying aluminium rod when it is placed in a magnetic field. It also suggests that the direction of force is also reversed when the direction of current through the conductor is reversed. Now change the direction of field to vertically downwards by interchanging the two poles of the magnet. It is once again observed that the direction of force acting on the current-carrying rod gets reversed. It shows that the direction of the force on the conductor depends upon the direction of current and the direction of the magnetic field. Experiments have shown that the displacement of the rod is largest, or the magnitude of the force is the highest, when the direction of current is at right angles to the direction of the magnetic field. In such a condition, we can use a simple rule to find the direction of the force on the conductor.
Okay, here it is written, experiment suggests that from the experiment it has been revealed that displacement of the rod is largest when the direction of the current at right angles to the direction of the magnetic field. And now we will just apply one rule which was given by the Fleming, and that is known as the Fleming's left hand rule. Few minutes ago I have told you the direction. I have told you about the direction. So now we learn about the in which direction it will be. Here it is written displaced towards left. So in which direction it will be displaced, we'll get an idea from the Fleming's left hand rule. Dear student, already I think you have understood why the current carrying conductor will be displaced. I think you have understood, because it is nothing but the interaction in between the two magnets. Very natural, quite natural, no problem at all. So if we consider this conductor as a magnet, then no problem about this understanding. We can understand the phenomena. Now we will just understand what is Fleming's left hand rule. So here it is written that, then we have to read all this portion.
We considered the direction of the current and that of the magnetic field perpendicular to each other and found that the force is perpendicular to both of them. The three directions can be illustrated through a simple rule, called Fleming's left-hand rule. According to this rule, stretch the thumb, forefinger and middle finger of your left hand such that they are mutually perpendicular, Fig 13.13. If the first finger points in the direction of magnetic field and the second finger in the direction of current, then the thumb will point in the direction of motion or the force acting on the conductor.
Okay, so now just applying the Fleming's left hand rule, you can get the idea in which direction the conductor will be moved or displaced. So first of all, what you have to do? First of all, you have to take your left hand. Now take your left hand. What I am saying, you just copy that. Take your left hand and take the fingers. Which fingers you have to take? First of all your thumb, then this thumb, then the index finger, that is called the forefinger, and the middle finger. The direction of field will be characterized by the index finger, and the direction of current will be indicated. The direction of the current will be indicated by the middle finger. Okay. So first of all, what you have to do? So again we have to go to the previous figure, and here you can see what is the magnetic field direction, N to S, that is north pole to south pole. So you have to align. So already you have just expanded your fingers 90° with each other. Three fingers, what I have told you, you have just make it 90°. Then in this situation you have to align your index finger according to this direction, that is from below to upward, the vertically upward. So you have to align your left hand, and which finger you have to align in this direction? That is field. Field will be indicated by the forefinger, that is the index finger. Okay. Then remaining finger. Now again in this situation you cannot change the direction of the forefinger, that is the index finger. You cannot change. Now keeping the index finger intact, you have to change the direction of the current. Now tell me in which direction the current is flowing? That is B2A. B2A means in this figure it is towards you. Then you have to just rotate your fingers, keeping the index finger intact. You have to rotate the hand, and how much it will be rotated? When your middle finger comes to your side, this thing you have to do. Then automatically when you just apply this formula, what formula? You have to align your index finger first of all along the magnetic field, and next you have to align your middle finger along the current direction. Then automatically the remaining finger, what is the remaining finger here? That is a thumb. So thumb automatically indicate that is this direction. According to figure it will be left direction. Okay. Now this portion,
Devices that use current-carrying conductors and magnetic fields include electric motor, electric generator, loudspeakers, microphones and measuring instruments. In the next few sections we shall study about electric motors and generators.
so this is the backbone of just using the motors. So motor is working in this way. You can see motors are used in different fields. Now example, now if you just read the example you can understand.
An electron enters a magnetic field at right angles to it, as shown in Fig. 13.14. The direction of force acting on the electron will be.
So now there are total 4 options, to the right, to the left, out of the page, into the page. So what is happening here? So two directions already given. Which direction already given? That is the current direction and the magnetic field direction. So we know always electron is a negative charge and current is conventionally always flow opposite to the electron flow. So here current is flowing from bottom to top. That current direction will be totally reversed here. That is the electron direction, but current direction will be opposite to it. And now take your left hand. Now align your 3 fingers, that is the thumb. If we go to this figure then you can understand. Now align your thumb, then your index finger and then the middle finger perpendicularly. Okay. Now first of all any of the directions you have to just match. Suppose magnetic field. So in this figure magnetic field is from the page, that is left to right. So we know magnetic field is indicated by the index finger. So you have to move your index finger from left to right. Yes. Then the directions of the magnetic field and direction of your index finger will be coincided. Then what you have to do, keeping this index finger direction intact, you have to rotate your hand, you have to rotate your finger. Which finger? You have to rotate your middle finger such a way it will indicate the current direction. Then you have to just rotate keeping the index finger intact, that is from left to right side. I'm just rotating my hand and it will be now upward, because now we have aligned the index finger along left to right direction and we have aligned the middle finger from vertically upward direction. Then automatically the thumb, that is the remaining finger, will be thumb. So thumb automatically it is giving the direction that is towards the page. So answer will be into the page. But answer when will be out of the page? If the suppose proton is moving, if instead of electron, if the question is giving proton is moving, then proton direction will be coincided with the current direction. Then keeping the magnetic field direction, that is the index finger, intact, you have to move your middle finger vertically downward. Then if you just keep your middle finger vertically downward and the index finger towards this magnetic field from left to right, then automatically your thumb will indicate towards you. Okay, towards you means that is out of the page, out of the page, towards you. Okay, so I think you have understood the answer. So thank you for watching my video. If you think video is helpful to you, then don't forget to hit the like button and subscribe my channel for next upcoming videos.